I know what your compiler did. Optimization effects on power side-channel leakage for RISC-V. And the talk is given by Durba.
Hello, yes. So hello everyone. So the title of my talk is I know what your compiler did, and I hope by the end of the talk you will know too. So I will give a brief overview of how we do a power side-channel attack. So far in this session, we saw timing side-channel attacks and EM. So in power side-channel attacks, particularly for software implementations, we have a software implementation of any cryptographic algorithm, which we build using a compiler and which we flash on a microcontroller or a microprocessor, and then we measure its power consumption traces. So here we have an oscilloscope which captures the net power consumption. We have a trigger signal which ensures where should we start with the power consumption. And then we get these traces, and next these traces are analyzed to see leaks. So now in the first step, which is the compilation, we have, this is basically the command that we see. So first we see the compiler, then it specifies the architecture, followed by the libraries, and followed by a character, which is OS. So this basically specifies the compiler optimization level. So even if we do not specify this level, it takes O0 as the optimization level, which states that the compiler will not make any changes to the binary file. Now, there are other variants. So there is O1, O2, and O3 for higher levels of optimization. So these basically optimize for execution time. And then there is OS, which optimizes for the code size, which is more prevalent for applications such as for like edge applications. So now the question that we want to investigate here is how do compiler optimizations impact power-based side-channel leakage? So first I would like to answer the why. Why do we want to do this, and why RISC in particular? So as we saw in our previous talk, so RISC is an open source instruction set architecture, which makes it customizable, scalar, and cost effective. And it has seen several adoptions in extensions of this instruction set architecture, as well as development of hardware accelerators, which can be paired with the core. And we have also seen the implementations of post-quantum algorithms like Kyber and Lithium. So now coming back to our question. So now we answer these questions, or we rather ask smaller questions to answer our complete question. So first we see what are the effects on the compiled binary. Next we see, can we isolate the compiler-induced effects? And the third question that we ask is, how does it impact power side-channel analysis? And do we see these impact or these compiler-induced leaks in real traces? And finally, can we somehow predict these leakages by looking at our data or our binary? So let's start with the first question. So for this, I would like to put this picture in front of you, which basically gives you a snapshot of an execution of an unprotected AES implementation. So here, I would like you to focus on the vertical lines. So here we have 7 colors, each indicating a type of an instruction. So we have load, store, branch instructions. So the lines which appear at the topmost level correspond to the unconditional branch. So they basically indicate where the function calls are in the implementation. And in particular, I would like to focus on this part, which is basically the shift rows operation of AES. So how it is implemented, it is basically implemented with a series of alternating load and store operations, where it loads the address, then the content, and it moves it back to a correct position in the memory, and so on. But now, when we change the optimization, so this is for optimization level O0. Now, when we change the optimization level for OS and O2, we see in particular for the shift rows operation that the number of instructions and the ordering of instructions change completely. So this is one aspect that we observed. Another thing that we observed that many of these functions are inline. So when we are optimizing for time, it wants to save on the unconditional branch operation. So it inlines a lot of code, which also results in more register usage. Sorry. So here we can clearly see the difference in the shift rows operation. And what it means that when we go from one level to other, the register usage and the allocation pattern is very different. And these are the architectural registers that RISC provides us. And since the register usage pattern is different and we are loading data in a different order, it will leak or it will lead to changes in the power consumption or let's say power leakage. So now the next question that we want to answer is, how do we isolate the effects of compiler optimization? So we have a complete power trace. So now this power trace that we get from an oscilloscope comprises of an operation-dependent component, a data-dependent component, a noise, and a constant factor. But now we are basically interested in only the component that comes from these architectural interactions. So how we do that is we can basically segregate, or just for our understanding, segregate the operation-dependent component into two parts, which correspond to the architectural based operations and the micro-architectural based operations, which come from the target device or the ISA implementation. And we say that we can basically just look at the data-dependent component and the architectural component. Now, to extract this component, what we do is we call as an architecture level simulation. So for this, we take the ELF file, which we run on the target device. We feed it to an emulation framework, which is chilling in this case, which provides us with an execution trace. So now this is how an execution trace looks like. So it consists of a sequence of assembly instructions that are involved in the execution. Alongside it gives you the state of all the 32 architectural registers after every instruction gets executed. So now this is a small snapshot showing only 10 instructions, but as you may understand that depending on the implementation, we may have thousands of such assembly instructions. So now we apply leakage models, which are Hamming weight, Hamming distance, and identity in our case, to these execution traces, and we get something we call a simulated power trace. So now this is an example of a simulated power trace of a first order masked AES. And here we can clearly see the 10 rounds, and we can also annotate the start and end of individual operations. And if I just zoom in the first round, we can clearly annotate the start and end of each of the individual operations. So now we come to the third question. How do these optimizations impact power side channel leakage? So for this, we use these architectural traces or the simulated traces. So the advantage of these simulated traces is, I will go back. So the advantage of these simulated traces is that the granularity at which we get each point is for every instruction. So now every peak we can associate to one given executed assembly instruction. So now whenever we do correlation analysis or any leakage analysis, we can really go back and attribute it to the cause or which instruction is causing that leak. So now when we want to understand how these optimizations impact power side channel leakage, we are particularly interested in evaluating masked implementations. So what we want to see how effective are masked implementations when we change the compiler optimization levels. So for this, we choose a first order masked AES, and we focus on the shift rows operation of masked AES, because we particularly saw that the ordering of instructions vary for this operation. So now we will go step by step. So we are focused on the first or the second row, which is colored. So now the first step, what the compiler does, it basically loads the first and the fifth byte into two registers. Then it stores the fifth byte into its updated position in the store at index 1. Then it loads byte 9 in the same register A4, which previously had S5. And then it again stores the value of byte 9 into the index 5. And next it loads byte 13. And after this, it loads byte 1 into the shifted position. And again, it stores byte 13 into the shifted position. So now what I want you to focus here is that we see a load, store, and a load interaction. So first we load the masked byte 5, then we store it, then we again load masked byte 9. Now what this does is, if we look at the expression for mask byte 5 and byte 9, so when we so this basically byte 9 overrides byte 5, and what happens effectively is that the mask gets cancelled, and we get an XOR of the unprotected subbytes output. So now we want to validate it using the simulated traces that we have. So we correlate this unprotected XOR value with the simulated power trace, and we see two peaks, one which appears at the shift rows operation and one which appears at the mixed column operation. And this we do over 5,000 randomly chosen traces, where we fix plaintext byte 5 and we randomize byte 9. And if we zoom into the assembly instructions which cause these leaks or which correspond to these leaks, we understand that this is the exact instruction which loads byte 9 to A4. So this basically helps us to annotate the leaks with assembly instructions. Now we want to understand, or we want to establish whether these leakages are also propagated in real traces that we measure from the target device. So for this is a snapshot of our experimental setup. So here we have a ASIC implementation of, we have an ASIC implementation of the Pico RV32, which is a RISC-V core with no pipeline. And we have this collection setup where we have the power generator, which supplies a power of 5 volts to the board, and we collect our traces using Chip Whisperer Husky. And then we perform the same correlation analysis using these real traces. And here as well, we see two peaks. But I would like to point out here that since we are looking at the trace for the entire AES, with some part involved in setting up the initial bytes, that's why we see that the two peaks are very close to each other. So now this confirms our validation that we actually see these architecture or these compiler-induced leaks in real traces, despite having noise, the constant factor, and other microarchitectural factors. So we also did this experiment for other optimization levels, and so we can confirm that these architecture level leaks are visible in real traces. So now we come to the last part, or a more interesting part that we are still exploring, is can we predict these compiler-induced leaks just by viewing these data interactions? So for this, I would like to first start with a toy example, where now these are 11 assembly instructions. And now if I focus at the first instruction, which means it loads the content of A5 to A4. So this is where in A4, I load the yellow data, let's say. And then in the second instruction, I load the content of A3 to A1. So at the second instruction, I load the data that we represent with green colors here in A1. And now there are no load operations which can change it. So now here we see, if we observe this register, until and unless some other data writes on this value remains in the registers, which gives us an indication now this becomes more prone to leakage. So this could be any intermediate or sensitive variable that we do not want to see. So this basically we term as remanence, how long a data remains in the architectural registers. So we count this in terms of the number of instructions. And another aspect that we observe here is that sometimes the bytes are overwritten and they reappear whenever they are required for further operations. So this reappearance, we call it as revival of the intermediate, or that the data gets revived. So now we count the remanence and revive for some intermediate. So here I show you the remanence and revive for the plain text bytes. So here each row corresponds to a given optimization level, and each column here specifies each byte of the state matrix or the plain text matrix. So now if we observe for OS, if we look at byte 0, this stays for 15 instructions. But if I look at byte 15, this stays for 450 instructions, almost 30 times. So we should be, so we can hypothesize that we should be seeing more leakage, or like we should be able to see this value for a longer period of time in our traces as well. So to validate that, we conduct this experiment where we correlate these bytes with the power traces, and we see indeed that when we are looking at byte 0, it appears or it correlates with a high value for only certain number of instructions. However, for byte 15, we see huge spans of time where the byte stays in memory and can, of course, be exploited. So this also tells us that we can track these data flow of the values through the execution to understand or to, so basically give an indication of leakage, or maybe the first steps in predicting leakage. So now, just to answer all the questions that we have asked so far. So what are the effects of compiler optimization? So we see on compiled binary, it causes strength reduction, where it changes more expensive instructions to more, less expensive instructions. There is instruction reordering and changes in register allocation. Then can we isolate the impact of these optimizations? Yes, using architecture level simulation. And how do these impact power side channel leakage? By introducing unintended interaction between shares. Do these effects propagate to real traces? Yes, we see them in measured traces for masked implementations. And finally, can we predict these leaks? So we say that these are the first steps towards the direction, but we still have a lot of work to do in this. And the takeaway that from this work should be that whenever we are evaluating any cryptographic implementation, the version of the compiler and the optimization level should always be specified. Even if we do not set it explicitly, the compiler sets a default version. So these should be taken into account when we are doing power-based side channel analysis. And thank you. And this is an archive version of the tool that we used to do this analysis. And I would like to take any questions that you may have. Thank you.
But compiler versions would have a similar effect. Have you done any experiments on that?
Compiler versions?
Yes.
Yes, we did some experiments on like 5 different versions of compiler, and we see that we see basically change. So this we did recently. So we observed some changes in the simulated traces, but we are still in the process of collecting data from the real target.
Thank you.
I was wondering, I didn't quite follow if I understand correctly from your analysis, that if the data stays for a long time in the register, that would be bad for leakage? Well, I thought actually the dynamic switching power of the registers is the most leaking thing in power trace analysis.
Yes, so we basically devise 2 metrics. So one is remanence, which can sort of predict value-based leakage, how the value remains in the registers. And for this transition-based leakage, we think we can understand it from revive.
Okay, well, we can ask it talk later also. And I had one other question: to what extent do you think this extends to more complex CPUs? Because I think you tested it on a very simple pipeline, right? And I guess it becomes way more complicated the more complex your processor is. What do you think of that?
As per my understanding from this work, these these compiler-induced leakages will still be there, because these are all at the architecture level. So even with more complex architectures, maybe the impact we see in real traces reduces, but we cannot say that it completely mitigates the compiler-induced leaks.
Thanks.
I might have missed it in the slide deck. Is there a public repo for this tool?
No, it's a work in progress. So yeah, but we will make it public soon.
Okay, thank you.